Okay, welcome everyone to another installment of our labs, this time lab 6, which will be looking at correlation and regression, what we just looked at in lecture last week. So first of all, to differentiate what is correlation, what is regression? Well, correlation is used to analyze whether any two continuous variables are associated with one another. And how we quantify the strength of that relation or correlation is through the correlation coefficient R. So with correlation, we're assuming that we're dealing with a linear relationship, a straight line relationship. And we have two measures of the correlation coefficient with correlations. We can either do a parametric correlation, which is the Pearson correlation coefficient, or if our data is not following a parametric distribution, we have to go with the non-parametric correlation, which is the Spearman's rank correlation coefficient. We're going to be using both of these to analyze the data set in today's lab. So that's correlation. Regression is a little different in that we're trying to, with regression, trying to predict how one variable will change another variable. And then the way we do this is we basically create a mathematical regression model to relate the dependent variable to the independent or input variable. So we use linear regression to predict new values for the dependent variable, giving a certain value of an independent variable. So with today's lab, we're going to be using JASP again, but we're going to be dealing with one data file that has to do with soil data that was collected in southern BC. So again, just a quick summary of the differences between correlation and regression. Correlation, we're measuring the relationship, the association between two variables. And then with regression, we're trying to see how one variable will change when another variable changes. So keep in mind that neither correlation nor regression imply causation. They can only show, with correlation, show an association, and with regression can show how one variable changes with another. So with correlation, right, we define the strength of correlation through the R value, whether that be the Pearson parametric version or the Spearman non-parametric version. And then with regression, we define or quantify the strength of the regression relationship through the R squared metric. Okay, so again, the data file that we're going to be looking at today in JASP is the CSV file core reg soil data. So this file contains a bunch of different variables relating to the chemistry of soils taken at different locations in the southern BC. So things like sulfur content, pH, calcium content, iron content, and the cation exchange capacity. These are the variables that we're going to be looking at in today's lab. So if you open up that CSV file in JASP, you can see those variables right there at the transect. So the first thing we're going to do, like with all our labs with JASP, we're going to be using JASP to define our descriptive stats, things like the mean, standard deviation, standard error, and skewness for all 5 of our different soil variables. Then we're going to be checking for normality. So we're going to be doing this visually through box plots and histograms. And then we're also going to be doing the Shapiro-Wilk test, again, using a alpha value of 0.05 to determine whether we're going to reject or not reject the Shapiro-Wilk or the normality null hypothesis assumption. And then based on those results, you're going to answer in 2E, do the data meet the assumptions required for a parametric correlation or regression, right? So if our data is normally distributed, we can go with the parametric correlation. If we find from the Shapiro-Wilk that our data is not normally distributed, we have to go with the non-parametric versions of correlation and regression. So once we get our descriptive stats and our test for normality done, we can run the correlation and linear regression models under the regression tab. So the first thing we're going to define is the null hypothesis, right? So you're going to answer there whether there is blank statistically significant correlation between the soil variables. So I'll just give it to you right now. that with the correlation, the null hypothesis is that there is no correlation between our variables. It's only when we reject that that we're going to find that we do have a significant correlation. So we're going to be running, for correlation, we're going to be running both the parametric and non-parametric correlation metrics for this data. So you're going to be basically filling out this table here, entering the Pearson's R correlation coefficient and also its p-value. So again, the Pearson's is the parametric version of correlation. And then you're also going to be running the Spearman's correlation tests, where the metric is the Spearman's rho, and then filling in the associated p-value for each Spearman's rho for each of these correlations. So between, say for the second one here, pH versus that variable there, pH versus iron, iron versus calcium, you're going to be entering the R values, the correlation coefficients, the associated p-values for those R values, and then the Spearman's rho and the associated p-values for those Spearman rho coefficients. So when you put your variables in the linear or the correlation module in JASP, right, you're going to put your variables in the variables section there. And then you're going to be selecting those two boxes to run the Pearson's R and the Spearman's rho. And so the way the data will come up, it'll come up in this table where you can get your Pearson's R and your Spearman's rho, right? So for example, between my SKGHA versus pH, right? There's my Pearson's R coefficient, which is minus 0.068. It has a p-value of 0.127. And then my Spearman's rho is minus 0.101 with an associated p-value of 0.023. And then basically you're going to be reading and filling in that table based on the rest of the information given in this table in JASP. Okay, so that's correlation. The second part of the lab is running a regression analysis. So with regression, in this example, we're going to be running regression for two variables, right? Calcium content and the cation exchange capacity of the soil. So we're setting up a regression model between those two variables. And so in this case, the calcium content, Ca kilogram hectare, is the dependent variable. And the other variable, the cation exchange, is the covariate or the independent variable. So you're going to be running the regression model in JASP, and you're going to be filling in for the M1 in the table, the R squared, something called the Durbin-Watson stat, which I'll talk about in a bit here, and the p-value. And then based on that, right, the p-value, does the regression analysis indicate a significant relationship between the variables? Again, the null hypothesis is that there is not. Only when we reject that null hypothesis is that we're going to say there is a significant relationship. Right, so once you're in the linear regression model in JASP, right, you're going to put your dependent variable in the dependent variable window. You're going to put what's called your covariate, aka your independent variable, in the covariate window. So basically with this regression, you're going to be setting up a regression model where you're going to try to predict the value of calcium in the soil based on covariate or the input variable of the cation exchange capacity variable. Okay, so that Durbin-Watson statistic is a test for autocorrelation in the residuals of the model. So in the lecture, I showed you how the scatter away or points away from the straight line regression model, right, tells us about what's known as the residuals, or the amount of error or uncertainty we have in our regression model. So what the Durbin-Watson stat does is that it does an analysis on these residuals to see whether there is a autocorrelation or not. Because we want our residuals or our errors to be random in nature. We do not want them to be either negatively autocorrelated or positively autocorrelated. Okay, so when we run a Durbin-Watson test, right, we start out with the null hypothesis that our data is not, or our residuals are not autocorrelated, and only if we reject that and we interpret our Durbin-Watson stat is that we could determine whether our residuals are positively autocorrelated or maybe they are negatively autocorrelated. So that's what you're also going to be running in the regression model in JASP. Again, the Durbin-Watson stat tells us whether our residuals are random in nature, which is our null hypothesis, or if we reject the null hypothesis, we're going to say that they're either negatively or positively autocorrelated. So the way that we interpret the stat that we get for the Durbin-Watson statistic, right? If we get a Durbin-Watson stat of our number of 2, right? That is telling us that we're going to go with our null hypothesis, saying that there's no evidence of autocorrelation. If we get closer to 0, we're dealing with positive autocorrelation. And if we reject based on a very small p-value, like below 0.05, we're going to reject the null hypothesis and say that we instead have negative autocorrelation. So if we reject our null hypothesis and we have a Durbin-Watson stat closer to 0, we're going to say we have a positively autocorrelated residual. If we reject the null hypothesis with the Durbin-Watson and we get a Durbin-Watson stat closer to 4, we're going to say that we instead have a negative autocorrelation. And so this is where we find the Durbin-Watson stat underneath the statistics tab in the regression model in JASP. And so in the table, as you can see here, under the Durbin-Watson heading there, right, you'll get your stat for the M1 model. That's the model that you want to use. And then you'll get an associated p-value. So again, the p-value is going to tell you whether you're going to reject or not reject the null hypothesis. And then the Durbin-Watson stat, the number itself, is going to tell you whether you're dealing with a positively autocorrelated or negatively autocorrelated residual should you reject the null hypothesis. And then to determine the regression relationship between your two variables, calcium and the cation exchange capacity, this is the model right here. So you're going to build your model based on the coefficients, basically your y-intercept, the value of y, in this case calcium, if you set the value of your cation exchange capacity to 0, and then also your regression coefficient or your slope. So those are the two values that I've blocked out there that you will use to construct your regression model between those two variables. So the last thing we're going to do to kind of complement the Durbin-Watson statistical test for the distribution of our residuals is that we're going to analyze them visually, the residuals. So under plots, click the residuals versus predicted, right? So this will give you a scatter plot. And so if our residuals line up to what they should be predicted, if there's no autocorrelation, right, they'll line up along the line quite uniformly. If they do not line up along the line, right, it is an indication that we're dealing with a autocorrelated residuals. The other thing we can do is do a QQ plot for standardized residuals. That'll also tell us whether our residuals are random in nature or whether they're autocorrelated. So if they do not line up very nice along the line, that tells us that we're not dealing with, or we are dealing with a very autocorrelated residual and not with a randomly distributed residual. So based on the plots that once clicking those two buttons gives you, right, you're going to answer the last two questions, 5F and 5G. And then the last thing you're going to do is you're going to save your JASP file, and you're going to enter and basically drop the JASP file into the Dropbox at the end of the lab. And that's it. So that'll be it for regression and correlation in this course. So we'll be talking next week, or later on this week, I should say, about non-parametric tests.